This video guide is meant to teach you how to linearize graphs. This is an advanced technique that you need to know in order to answer some types of questions on the AP Physics exam. It's a way of validating a nonlinear relationship. We use the correlation coefficient, and that's often really helpful, but sometimes you'll have points. And when you try different graph shapes or trend lines, you will get equally good correlation coefficients. So often that's just not enough information to help you figure out which graph shape is best. In addition, when you're hand plotting graphs, how do you know, right? You don't have access to a correlation coefficient. How do you know what shape the graph should be or what relationship you're actually getting? So it's a great way to tell if a complex function is a good fit for a particular data set. And we can also use the slope of a linear fit to gather all sorts of other information. And also there are some shapes that are so similar you can't distinguish them. So for example, 1 over x and 1 over x squared, when you hand plot, or even if you make an Excel plot, you can't see the difference. You can only tell once you put a function on it. And sometimes they'll be equally good, so you really have to validate it. First, as always, you make your normal graph. You write out your mathematical model. If it has a best fit curve with a nonlinear function, then you're going to do the following. All right? First, you're going to make a new column in your data table for the independent variable as it's written in the mathematical model. Then you're going to populate that column by performing the function on the independent variable. Well, here's the thing. If you have a nonlinear function, then you have to do that particular function. So if the function is x squared, then do x squared. If your function is x to the negative 1, then do x to the negative 1 to that variable. So you're going to do that in your data table and actually do the calculation. Well, what happens if you have a function and you do a power fit and you get 0.9, it's x to the negative 0.902. Well, you have to round that to the closest function that we deal with in our class. In our class, we only deal with positive or negative 1/2, positive or negative 1, or positive or negative 2 for functions. So you have to see, well, which makes most sense. You might need to look at the theory, or you might look at what rounds closest. Then you make a new graph of the function of the independent variable, your new column, versus the original dependent variable. Evaluate the linear fit and determine if it's valid. So here's an example. So let's say we had measured the initial height of a projectile, and you measured the range and got these averages for your range. And you plotted them, and you got a trend line fit that was to the 0.4855. Okay, so you'll notice that this mathematical model is pretty close to the exponent is close to 0.5. So you would want to redo, I gotta move this out of the way, sorry. You would have to redo your x-axis variable, so your height, to that 0.4855 power, but we don't use 0.4855. It's going to be to the 0.5. So you're going to make that, right, height to the square root, or height to the 0.5 power, and you do that on your data table. Then you plot the square root of height versus your range, and look what happens. You get this great straight line with a really good r squared. That's a good fit. That shows that range is directly related to the square root of height. So here's another one. So in this one, we have a cart moving up and down a ramp, and we were measuring energy. So we graphed here height versus velocity. Okay, so we've got height here, and we have velocity here, and when we graphed it, we got this quadratic that had a really good fit. Okay, so looking at that first part of the mathematical model, right, you've got to the y to the x squared, and the other terms are not so important. We're really looking at the biggest term, this x squared. Okay, So then when we go to back to our data table, we're going to do velocity squared. So we're going to take this column and do that squared and make a new graph where on the x-axis we plot velocity squared. So we're only manipulating our independent variable to check this. The y variable, the dependent variable, doesn't change. When we do this, notice again what a great linear fit we get, right? Like, yes, we have slightly different trend lines for each half of this motion, but it's really close enough. We get this 0.99 value for our r squared value, telling me that that velocity squared is directly related to the height. What if we had mass versus period for an object oscillating on a spring? So we do this lab. We didn't do it yet this year, but we have this lab. We put it. We take a mass and we hang it. I mean, we have a spring. We hang it. We hang a mass from the end of the spring, and we set it in motion. We measure the period, which is the time for it to go, make one complete cycle. So we have this period for different masses. And when we did this, we got, we have these three possible trend lines. And you'll notice that the r squared values are all pretty darn good, right? How do you know which one is correct? So you have to do a mathematical model, test them. You don't redo your linear one, right? But you want to see if you do this square root one, or if you do the squared one, does it give you a better fit than the linear trend line? So when I did the square root of the mass, right, you'll notice I made two more columns. I did the mass squared and I did the square root of the mass because that was my independent variable. When I did the square root of the mass, I got this great trend line with an r squared value of 1. When I did mass squared, look at what happened to my trend line, right? My r squared value is terrible. I can see that this data does not fit. So then my choice would be, right, well, this is definitely a better fit, and it's even better than my original linear fit. So even though this had a 0.94 correlation coefficient, this is obviously much better. So when is linearization not going to help? Well, if you have too compact a data set, it's going to be pretty much the same no matter what. And I've talked to you about this before, where you have to spread out your data over a wide enough range so that you can tell what's going on. Because sometimes if you have a curve, right, any segment on that curve is going to give you a straight line. And so it will seem like a good fit regardless. So you need to, and sometimes you can't help it, but sometimes it's because you picked poor data to test. So that's why I'm always encouraging you the smallest value possible, the biggest value possible, and then 3 in between. So make good choices in your experimental design, and linearization will help you to really nail down that best fit trend line. So what do you have to include when you do it in your lab report when you do this? So you can include your original graph, you can include your linearized graph. I don't necessarily need the original graph, but most people like to include it to show, to validate it, and that's fine. And sometimes the original graph, it's easier to interpret theoretically, but you don't always have to. It's up to you whether it's going to be helpful or not. It's just another piece of analysis that you can do that's more sophisticated and will help to give you a really strong CER.